Hello everyone, welcome back. Today we're going to talk about the concept of work, which I have already stated is the second most important definition in the course. Let's bring that definition back up. Work, a transfer of energy to or from the system. Now, before we go on, we've talked about the concept of a system before, but there are a few topics where recognizing your system and stating it are more important than energy, mostly due to this definition and the concept of work, because the only way to tell if energy is entering your system or leaving your system is if your system is very well defined. In our last video, we also put up the mathematical relationship, which I made unusually large, and we'll be working with that today. So before we go forward anymore, let's bring up the units for energy. The SI unit for energy is known as the joule, or joule, depending on where you're from. And just to give you an idea of what you can do with 1 joule of energy, you can take an apple and raise it approximately 1 meter into the air. Another unit of energy you may be familiar with, depending on what country you live in, is the calorie. Now, people usually relate calories to food, but the truth is, it's just a unit of energy. So in other words, the gasoline in a gas tank of a car has stored energy. That energy could be calculated in joules or calories. And I, of course, would never recommend ever drinking gasoline. So I'm going to take our work equation, put it in the corner so we can reference it, and let's put up a pretty simple example. So here I have a shopping cart on flat ground. Our system is just going to be the cart. So we're only concerned with energy that is either entering or leaving the cart. Now to start out, let's say someone pushed this cart with 40 newtons of force to the right for a distance of 3 meters. Work is force parallel times displacement, which is 40 newtons times 3 meters, which is plus 120 joules. And as you may have guessed, this is an increase in kinetic energy, because as we discussed with our definitions, kinetic energy is the energy of motion. Right now, during this second distance, no one touches the cart. So if no one touches the cart, there's no force to the right, no force to the left. We'll assume it's frictionless, which means the kinetic energy here is 120 joules during this entire time. The cart is not speeding up and is not slowing down. Let's say during this displacement, which is to the right of 7 meters, there's a force exerted on the cart to the left of 5 newtons. Work is force parallel delta D. In this case, it would be negative 5 newtons times positive 7 meters. Notice both my displacements are to the right, which would give me negative 35 joules. Now we have something different here from what we've seen before in the course. Energy is not a vector, it's a scalar. Energy does not have a direction. If someone asks you how many calories are in that hamburger, you're not going to say 300 calories to the east. So now the question becomes, what do the positive and negative mean here? Well, since work is a transfer of energy, the positive and negative represents what direction the energy is being transferred. A positive work means that energy is being transferred into your system, which is the cart in this case. A negative work means energy is being transferred out of your system. So in other words, 35 joules of energy are being removed from the cart. What kind of energy is being removed? Well, again, kinetic energy is being removed. So a question that could be asked, does the cart come to a stop? Well, if it had 120 joules, we just lost 35. In this next section, I'll say kinetic energy final would be kinetic energy initial, would be this over here, plus the change in kinetic energy, would be 120 minus 35, which give me a kinetic energy of 85 joules. So the answer is no. This cart would not come to a stop. It would be moving slower, which is something we'll discuss when we talk about kinetic energy. But the big takeaway here is this relationship follows the vector directions. Here, positive force, positive displacement. Here, negative force, positive displacement. If I had, let's say this cart was at rest, force this way and displacement this way, this would give me a negative times a negative, and I would get a positive work, a positive transfer of energy. In other words, if the cart was at rest and you pushed it to the left, the force would be to the left and the displacement would be to the left, and the cart would speed up to the left, which means an increase in kinetic energy. In other words, all forms of energy are scalars, including kinetic energy. You either have it or you don't. And if you're increasing your velocity, you're gaining more kinetic energy, no matter what direction you are moving. Okay, next up, let's say we have a toy car. You push the toy car at an angle to the ground. We'll make it simple. Angle. We'll say the angle is 30 degrees. and force hand on car is 6 newtons. Well, a key point here is I need the force parallel to displacement. So let's say the displacement is 2 meters. The 6 newtons is no good to use because it is not parallel to displacement. What do you need to do? Well, you need to do what I said you need to do every time you ever get a vector in this course at an angle. You are always, always, always breaking it up. In this case, however, I do not need the perpendicular force. I want the parallel force. So this is the parallel force here. So I'm doing 6 cosine of my angle, which is 30 degrees, and I get 5.2 newtons. Force parallel times displacement gives me positive 5.2 newtons because it's to the right. My displacement is also to the right, so it's positive 2 meters. And I have an energy transfer of 10.4 joules. A quick word of note, you will often see the work equation written like this. Be very, very careful of this. And for now, I don't even recommend you think of it like this. Here's why. Let's say I have a sled. I have a force pulling my sled. Only instead of the angle off the horizontal, you were given the angle off the vertical. Now in this case, you still want the force parallel to displacement, which again is to the right. So in this case, you do not want the cosine. You want the sine, the opposite side. So this angle is assuming it's off the x-axis. But if someone really wants to assess if you know what you're doing, they will simply switch the angle and put it off the vertical axis. In other words, I recommend you do not rely on this. Rely on this relationship. You are after the force parallel to displacement. Look at the situation and figure out how to get it. In other words, draw the vector breakup, then go after whatever side you need. Because setting up a problem like this is the easiest way to catch to see who knows the physics and who is just following the mathematical formulas. All right, in our third case here, there's a few things we need to chat about. This is a barbell, just like you would find in a gym. You're going to lift the barbell into the air. That means you are lifting the barbell and you are separating it from the earth, which means we are going to be dealing with gravitational potential energy. Now that means our system is going to be the barbell and the earth. Now we're going to find the energy transferred into the system by you. So these objects are in the system and you are not. Notice you were not in the system in any of these cases. But before we do this, there's something else we need to discuss. I want to do a force diagram of a lift. And to really get the point across, I'm going to say force Earth, which is the weight of the barbell. I'm going to use the units pounds. So this is a 100-pound barbell. To start out, if you were to hold this barbell in place so it would not move, force hand on barbell would need to be how much force? Well, it would need to be 100 pounds. Let's say your goal is to lift it upward 1 meter. Now, in order to begin the lift, these forces need to become unbalanced. So, for a small distance, this force would need to be greater than 100 pounds. In other words, you would need unbalanced forces to change the velocity of the barbell, hence Newton's first law. Now, once the top of the barbell actually reached here and had a velocity, for most of the lift, you are lifting at a constant velocity. So, for this beginning period, your acceleration is upward. For this middle period, your acceleration is 0. Now, that means during the second period, during the lift, how much are you pushing with? Well, if acceleration is 0, that means you are lifting with 100 pounds. In other words, the barbell is still moving upward at a constant velocity, but your force matches force Earth. Via first law, this must be true. During the very end, the barbell needs to slow down to a stop, which means the acceleration has to be downward. How do you do this? Well, you merely push a little less. You push with a force that is less than 100 pounds, a little bit. That means force Earth is larger than force hand on barbell, and it slows down to a stop. Once it comes to a stop, again, you match 100 pounds of force. Now, I'm mentioning this for 2 reasons. 1, this means that during the lift, for the first acceleration period, you need to lift with a little more than 100 pounds. During the constant velocity period, you need to push with 100 pounds. During the second acceleration period where it slows down, you need to push with a little less than 100 pounds. So, little more than 100 pounds, equal to 100 pounds, little less than 100 pounds. That means, what is the average force you are being used to lift That means what is the average force you're using to lift the barbell? The average force you're using is 100 pounds. During the acceleration period, you may be pushing with a little more, a little less, but your average is still 100 pounds. That means to lift an object, the average force you will use is equal to force Earth. That also means that this force parallel is an average force. That is important here, and it's going to be very important when we deal with elastic potential energy. So not only does the force have to be parallel to the displacement, this is also an average force. And to lift an object, the average force you use is equal to force Earth exerted on that object. The second reason I bring it up is because what kind of energy is being transferred here? The type of energy being transferred is gravitational potential energy. And people say, well, the barbell's moving, so isn't it kinetic energy? And the answer is no, and I'll tell you why. Your initial state is when the barbell is at rest, here. Your final state is when the barbell is at rest, here. In the initial state and the final state, the barbell is at rest, which means in neither case are you dealing with kinetic energy because the barbell is not moving. Is the barbell moving during the lift? Yes, particularly during this section when it actually has a velocity. And does it have kinetic energy during here? Yes, but our problem is not over at that point. Our problem is over when it's lifted and stopped. Sometimes you'll see a problem where they specifically state the object is moving upward at a constant velocity. Well, if the velocity is constant, that means the kinetic energy is not changing, which means you still don't have a transfer with kinetic energy because it's neither being gained or lost, it's constant. However, if the object is separating from the Earth, that means gravitational potential energy is being stored. So, back to our barbell. You are lifting it from here to here. Let's say the barbell has a mass of, make it easy, 10 kilograms. Force Earth is mg, would simply be 98 newtons. And as we just described, the average force you would use during the lift would also be 98 newtons, a little more at the beginning, equal to 98 during the lift, and a little less at the end, which means the force would be positive 98 newtons because you were pushing upward, we're doing the transfer from you. And let's say we lift this 1.5 meters. Upward, so it's positive, and we would get a transfer of 147 joules, and this would transfer into gravitational potential energy. When I do my video on gravitational potential energy, I will discuss why force Earth is not coming into play here, so don't worry about that. I just want to separate it in a different video to make sure it's very clear. But the big takeaway of this video is about work, which is a transfer of energy. In our first situation, we transferred kinetic energy into the cart. We talked about vector directions and the fact that transfer can be positive or negative. Positive means the energy is moving into your system. Negative means being transferred out of your system. With the toy car, we concentrate on the fact that it's a parallel force. So if your force vector is at an angle to your displacement, you must split it up and you are looking for the parallel portion of that force. For the barbell, the average force used to lift something is equal to force Earth, which means if you're ever dealing with a problem where you're lifting something straight into the air, you basically want to find force Earth, which is mg. All right, I'll stop here for now. Have a good day. This is Mr. M signing off.